Hi, I'm Edward. Thank you very much, Phil, for having the courage to have me here. I've been attending his meetups for donkey's years. I know, how long have you been doing it for? About 10 years, something like that? 9. Well, good enough. I'm Edward Boggis-Rolfe. I'm chief engineer of a company called Secretarian Limited. And I've been basically playing around with code generators, linking systems together for donkey's years using IDL principally as one of my favorite things to do. Lots of claims to fame. But anyway, I'm going to be basically talking about RPC, principle behind it, why it went out of favor, and what I think we can do to make it better. Thank you. Oops, clicker. Yeah, that helps. This is really quite far more kind of a status symbol. Right, okay. Is it working? Yeah. So you're probably all familiar with RPC, but just a quick reminder. The idea has been around for donkey's year. The idea is you want to be able to call a function as if it's a local function on your computer, but the actual function gets executed somewhere else. It could be remote machine or in a different address space, somewhere. It doesn't matter. And typically you have an interface specification file which generates proxies and stub code, which generates your function call parameters into a stream of bytes, and then you go over some form of transport, where it then gets deserialized, the function gets called, and then return again. It's been around since probably when I was a small child, at least, probably even longer than that. So a little bit about my company, because this gives a quite good use case as to why we want to use it. So we are a company that specializes in confidential computing, primarily in Intel SGX enclaves and TDX, by which you host applications in an environment where you can't access the computation by debugger or any other form of nefarious means. You then shove it on some form of server, and then you can connect to it using some form of remote attestation to communicate with the apps. So for instance, web browsers or host-to-host communication. And then you have to have all the additional kind of accoutrements such as remote attestation. So when you connect to one of these binary blobs, you need to have some form of digital signature that proves that the code you're talking to is the code you think you're talking to, and it's not running in some form of emulator trying to trick you into stealing your data. We also implement a raft network solution where we have leader and follower nodes so that we can deal with the kind of rollback attack, which is one principal part of security. Not an old idea, not a new idea. Things like Ethereum and things like that have been doing it for some time. So yeah, operating system has no access to the system, so you can have it on somebody else's machine. You don't trust, but they can't actually see what you're doing. They might turn the machine off. They can't do very much more to actually interfere with your processing. And then we have a platform as a service on which you then run WASM apps, which then use our environment for doing all that kind of sexy stuff. Okay. So how does RPC work? So multiple different interface definition languages. The big ones was COM from Microsoft, another one was CORBA from International Consortium. Those two absolutely hated each other. Another one here is the Java equivalent, forgotten its name now. So basically, you have an IDL file that produces proxy stubs, which call various serializers, metadata if you want, reflection, whatever it is. Some of these libraries also provide their own transport as part of the actual solution. Right, well anyway, this all became to a great big crescendo around about the middle of the 1990s. Microsoft had a technology that you might remember if you're old enough called OLE, Object Linking and Embedding, by which you embedded Excel spreadsheets into Word and things like that. The idea was they wanted to have Microsoft Office as a dominating application that wiped out all the competitions like WordPerfect, Amy Pro, Lotus 123, which then was using inter-process communication, and then they made it a bit longer from DCOM to communicate with other machines. Meanwhile, large alternative institutions, they came up with CORBA, primarily, and they absolutely hated those guts. Funny thing is, though, they were so keen on their own particular solution, they didn't actually notice that thing called the Web 2.0 came along, by which people were using things like SOAP, which is XML over HTTP, and then REST, eventually WebSockets and HTTP2 and all that sort of stuff, and it killed this technology dead. It became completely unfashionable. So we had all sorts of problems with version hell, blocking I/O, and of course they also used their own custom ports, which system administrators didn't like opening up because they were insecure, especially DCOM. By the way, I was using Nano Banana, so I apologize for that particular graphic. But anyway, I thought it quite liked it anyway. So what I'm trying to do here is address these concerns. So no vendor lock-in, backward compatibility. So as we evolve the application technology, we can connect to older versions of the same thing without breaking it, as well as you writing your own interfaces to your own applications and being able to let older clients connect to your new apps and vice versa. Eventually, maybe if somebody's got, I don't know, Tractor or something and translate into Rust, I'd be honored if they could do that. Fantastic. Network aware, so things break. You've got to handle the errors. It's a normal situation. Asynchronous. Conventional RPC from the 1990s is blocking. Doesn't scale very well. And I also want to make it format agnostic. So if you want to use RPC with JSON, proto buffers, flat buffers, any other binary format, MPI, you name it, you can use it. So it's separation of transport from format. So you can mix XML with HTTP, and you can call that SOAP. You can mix JSON with HTTPS and call it REST, or flat proto-buffers with WebSockets and call that gRPC, whatever it is. You can blend your way through. Some of this stuff's complicated, but the idea is separation concerns. Try and get these different concerns in their own little buckets. So you can, a network security guy, he just worries about the network security. Application guy just worries about the application. Margo. Right, here's an example. So basically, we define interfaces like this. Please use a namespace. We want to talk about later on about fingerprinting. By using a namespace and another version namespace and then your interface, it allows you to have future versions of interfaces which don't break old interfaces. This status thing here, you set it to production, you can then tell your CI system that the digital signature of this interface must not change once it's that particular status. So if you then try and change that interface, change something from const to non-const or something, it will be rejected. You also notice you can pass data in, you can get data out, you have to use attributes. You notice here, RPC shared pointer, you can actually pass interfaces to other objects that you may have elsewhere in your network of nodes, or you could connect to a factory and get back an ephemeral object specific to your particular needs, all that sort of stuff. We also have a thing called tags, which means actually communicating with the underlying transport protocol saying this function's special, such as in Raft we have queries, transactions, non-transactional queries, and that sort of stuff like that, which need special processing when you're actually dealing with in the Raft environment. Types, well, enums are treated as enum classes in C++, maybe something else in other languages. Kind of structures, we can embed your own types, std vector, maps, whatever it is you want to do. You can also put in things like static variables, which then not actually used by the underlying marshalling code, but then trickles right through to the actual generated piece of code that you're using. Quite useful. Something a bit more complicated, you can actually use templates in your interface definitions. So an example of one of our cryptographic libraries. We can do some funky stuff here, and that can be marshaled through quite happily. Okay. So anyway, facades. Facades are where you can inject code into your interfaces. It's quite nice. So you can do things like, let's say you want to make a database view set to a database, and the underlying interface you want, for efficiency reasons, you want to download. You want to iterate through the records one by one, but it's more efficient to download 100 at a time. So you can put in a facade by which you iterate through your records one by one, but behind the scenes, it's going off and doing all like a buffering, that sort of stuff, and all the internal state that you shouldn't be fiddling around with is private. Yes?
Sorry, in case I'm confused, when you said, like, you showed the template in there, it means that that template will transform in appropriate data structure, whatever is template in the other language, right?
Yes.
Okay, thank you.
Now, if you are trying to use Java and they don't support whatever language and doesn't support template, then you shouldn't be doing that. Think again. But anyway, it depends on what your goals are. But if you're just using C++, do this. If you're doing something else, maybe a simpler data structure might be suitable. A lot of these types here, for instance, an SED vector, obviously is not recognized by other languages. So the idea is what you can do is you can make your own definitions that then get translated into individual types. So this doesn't have to be an SED vector. We could have something like an RPC vector, which is converted into whatever underlying language type you want. But it resolves down to something where we have a common serialization format, whatever it happens to be. So anyway, here we got implementing a remotable class. So all classes derived from particular interfaces. Yes, I'm using virtual functions. I know they're not fashionable, but on high-end servers, actually, you could argue sometimes it can be a zero-cost abstraction. But anyway, let's argue about that in the pub. But it's just a very convenient pattern. I've been using it since the 90s, and I like it. Now, when you're implementing your remotable class, you define a class, you derive it from your interface. What you need to do, and you can hide this, I got some nice little examples of some syntactic sugar templates that hide all this stuff, is a means for the underlying runtime to get the most derived version of the class, so you can then cast through the other interfaces. And then you have some way of saying query interface, the interface ID, do you support that? And I'll show you the use case of this a bit later on. But then the rest of the functions is whatever you define inside your interfaces. Oh, go back here, sorry. Yeah, you can also variadic templates, so you can have as many interfaces as you want. It's quite nice. So service proxies. This is the actual glue between various logical units, apartments, or zones, as I call them, in your application infrastructure. So each zone is its own logical unit of objects. So you could have SGX enclave, which is in its own address space. And then you could be talking to the host application that's running that enclave. And then you could have some form of TCP connection to another machine. So that is talking to something else, somewhere else on the network, whatever it happens to be. And you have a variety of different types of service proxies. So they all basically derive from a particular interface called iMarshaller. So basically 4 functions. So the simplest implementations of service proxies, you just need to implement these 4 functions. Send, add ref, release, and try cast. This is all the RAII stuff going on behind the scenes. But you can also, we've also implemented inside the company, for testing reasons, local service proxies, but then we have host to enclave, enclave to host. I've also implemented, in the next version of RPC library, single consumer, single producer queues for inter-process communication, for asynchronous stuff. TCP, we're actually working on a new version of remote attested TLS. So when you're having enclaves talking to each other, you have to have some form of protocol injected into TLS to be able to attest that you're actually communicating with an SGX environment and not somebody pretending to be an SGX object. Other ideas, RDMA, kind of message passing interface, HPC stuff. Polymorphic resource allocators, so things you could have deterministic transactional memory for things like guaranteeing that every application will fail consistently when they run out of memory, which is quite useful for transactions. Maybe you have something for GPUs, whatever. But the RAS, I'll be giving you the slides afterwards, but this is a spec which we have the RA-TLS protocol. Now, if you're actually wanting to make a web gateway into your application, basically you have your web browser, what it is, and it injects your JSON or your flat buffers or proto buffers into here, and your gateway will route up to where your application is, and then that can go off to somewhere else, whatever they need to gain their services. So using it, this is a rather complicated function, apologies, but basically the service class, which is the thing that manages the zones, you can say to it, call this variadic template function, connect your zone. You then specify what type of service proxy you want, and you then need to provide it with a unique ID for that zone. Then you can pass in an interface. You don't have to, but for the code inside or for the remote service to talk back to you. And they have an out parameter, target in this case here, for the remote service to give you an interface. You can talk to whatever object you have on the other side of the thing. Now, because this is a local child service, I just simply got a lambda here, so this is actually the code inside of this thing running in a separate zone. So all communications between the outer app, the outer zone, and the inside get marshaled and demarshalled directly. But this could just as easily be, for instance, enclave. It could be the path to the enclave file, or it could be a TCP address, or whatever it is. You can put in whatever certificates you want, depending on whatever your implementation or service proxy. And you're encouraged to copy what we've done, amend it for your own particular use case. Okay? And this is what you're waiting for. So basically, you get your interface, you can call a function. There we are. So this host could be either local in-memory object using a normal virtual function call, or it's a virtual function call to a proxy, which goes over whatever transport you have, or several transports, many hops, to your application, and then it's, in this case, it's passing back an app object. We also, the new version of the RPC library supports coroutines, identical structure, except you have co-await inside there, or a conditional compile, capital letters, and you can do the same sort of thing. You can also, once you've got interface back, you can then do dynamic pointer cast. So this is a similar sort of pattern as a normal STD shared pointer. I tried to copy the idea to help adoption. So I'm just saying cast app into I bar, and you get back the bar. So cooking apps and bars, whatever it is. Never mind. Casting. Right. New features. So basically, version 2 has been in production with our company for a couple of years now, occasionally buffing the code from time to time, but new version coming out, and its two primary enhancements is coroutines. I'm currently using libcoro because it's small, and I'm trying to port it onto an enclave environment. Now, I would really love to get Unifex working, but that's a much bigger library, and I just don't have the time to address that. But it'd be nice to have IO-Uring eventually running inside SGX enclaves, and then enclaves become a zero-cost abstraction. It'd be quite cool. I need to do some patching on the SGX library because they don't support exception pointer, but we'll get to that. Optimistic pointer. Now, this is another thing. So you can have a share pointer, you can cast into an optimistic pointer and vice versa. It's basically a callable weak pointer. You don't really want to lock an object, a weak pointer, call it, and unlock it, because that means there's a lot of traffic going backwards and forwards. What you want to do, call the pointer, and if it's not there, you get back an error code. It failed. Fine. You live with it, move on. And functionally, they're very good for things like if you're an enclave and you have a pointer to the host is always going to outlive you as an enclave. So you have an optimistic pointer, so you don't have a circular dependency problem. Or if you're connecting to a remote web service and it's just always there, you can optimistically call it, it's just there. You don't lock the lifetime of that remote service. It doesn't mean anything to it, it has its own lifetime. But you can cast between them if your service proxy allows it. Weak pointers are actually pointers to the proxy, so they're not actually that useful. I use it internally. You're welcome to have it, but it's not much use. And unique pointers I've removed simply because you cannot guarantee exclusive ownership of that remote pointer. It just doesn't make sense. Now, if you disagree with a pint of beer, we can talk about it. So the synchronous version of the code can support C++ 17, and I'm aiming for C++ 20 for coroutines. The idea, we've got to work with austere environments where compiler and STL support is pretty limited. So I'm trying to use the minimum amount of support that whatever environment you're working in. You notice actually I'm returning error codes rather than using things like expecteds and stuff like that, because these are newer language features that, for instance, SGX enclaves just don't support. The error codes themselves can weave themselves into the error code system of the existing application. So you can allocate it a block of error code numbers and it will slot itself in. So you can then relay error codes of the underlying application along with error codes from the RPC side of things. Okay, so I got one little demo. Well, two. So I'm going to switch screens now. Hope you can see my screen. Here we are. So first one is basically when I'm running my tests, some of the tests are quite complicated and I want to get lots of telemetry. So I got really good logging, but it's all via this telemetry service interface, and if you turn it on, you would not want it in production because you'd leak everything, but it's quite good at talking to various telemetry servers which can actually do stuff with it. So for instance, I've got it to generate state transition diagrams or a lifetime of various objects. You can actually diagnose why things are going wrong. And I've also got this, it's quite good fun, so let's get this going. F11. Oh, how do you make the buttons are not working? Oh, wrong button, there we are. F11. Well, never mind. Anyway, I can just run it anyway. So I'll be falling asleep. So I'm going to start this. And can I get it smaller? No. Oops, I've now lost everything. Stop, reset, F5. Right, okay, well, let's just start again. So basically this is showing various zones. The host is spawning various zones. Each zone could all be either in-memory objects, or it could be a remote service, or it could be an enclave, whatever it happens to be. And so you've got to see here, this is actually just managing the lifetime of the zones. It's not actually showing much anything else. So anyway, I think blues are the actual implementation object, and yellow is the interface proxy to some other object somewhere else. I'm not going to zoom in because I'm going to lose the screen again. But this is actually a pre-recorded output from the logs. Oh, it's getting too big now, sorry. Anyway, never mind. It's quite nice. As you get to the end of the demo, it then kind of cleans itself up as well. Oh, never mind. But you get what stop. Oh, I probably crashed the browser now. But anyway, you get what I mean. Oh, is it working? Oh, it's carrying on working. Good. Try and get it to shrink. Yeah. Oh, that's a big test. So this was actually meant to be a hierarchical V or Y-shaped collection of things, but I vibe coded this on Saturday. It's not actually meant to be for normal production use, but I thought it would be good to visualize what was going on behind the system. Okay, cool. Oh, enough of that. Any questions?
I have a question.
Yes.
So it is, if I understood you execute parts of it on different machines and stuff, and you at the same time you talk about pointers.
Yes.
Right. So what is that? Like, is it? It's not one address space for all machines. Well, what?
No, the separate address space. So basically, when you connect, you want to get connection to a remote object. It could be in Timbuktu as far as you care. What you get back is a reference, like a remote reference to the object, and is represented as a proxy to that object that implements exactly the same interface functions as what a remote object is. So you call those virtual functions in your proxy, and the parameters get serialized, sent over the network, deserialized, and that function gets called and back again.
And every proxy has its own reference count, so it's this kind of distributed reference count. Sort of.
Yes, if you want it. If you want non-reference counting things, use the optimistic pointer approach.
Okay, cool. Thank you.
Microphone problem.
Yeah. Oh, hello. Yeah, perhaps related to the previous question, but you about 5 slides ago, you mentioned the shared address zone, shared,
yeah, well, you got
shared object
well,
space or something.
Yeah,
that one.
Sort of
No.
Yeah, well, this one here, we got a local child service proxy. I wanted to show everything in one screen. So this one here is mainly for tests. But here we got this lambda here. You wouldn't normally write, if you're trying to connect to a remote object. You'd be passing in an IP address or something. But this one here, I just want to show you, this is what you'd have running on your remote server. And in here, what you're doing is you're getting your host pointer. This is a proxy. That's the original object. You call that function, the functions in that object, it actually gets serialized and sent back to here, and deserialized and called. So this could be on a different machine as far as you care. Okay. And vice versa, and this is passing a reference back again.
Oh, okay, so there is no shared address space or anything like
no,
that. Yeah.
No, that
kind of related. Oh, all right, thank you.
Cool. So we'll go forward again. Oh, by the way, I'm going to be putting on I created a Discord server yesterday to put in the PowerPoint presentation. I'll do that after the call, or after the meeting. I think that's it. Yes.
Yep. I had another question about the coroutines. You had the optional conditionally compiled macros. What happens if you don't have coroutines and you call one of those then?
Well, you don't compile it with that flag. So we've got a number of different compilation flags in CMake. So if you build coroutines equals off in your CMake, then you won't build it.
Right, but I mean, what actually happens at runtime when you invoke?
Well, at the moment, this is still bleeding edge stuff. It's still work in progress. What I would like to do is to have coroutines and synchronous calls in their own separate RPC namespace. So it'd be RPC synchronous or blocking, whatever you like to prefer calling it, and RPC coro. And then you can then basically choose whatever you want, and then you can have conditional compilation in the hash include of that. So basically a hash include twice, but with different compile flags going, or hash defines going through both, so you can have both running side by side. So if you want to bridge between a asynchronous and a synchronous call stack, you do so.
Okay, thanks.
Once I think synchronous, it becomes synchronous. It stops doing proteins.
Sorry, I misunderstand.
I believe the answer to Phil's question of what becomes when the coroutines are not available is that the API call is synchronous.
It just doesn't exist. You just compile it so it doesn't have coroutine support. So for instance, I need to compile it for C++17. So you just say build coroutines equals off in your CMake configuration, and they just don't exist.
Yeah, but you have a call wait macros that does something.
Well, the macros just resolve to nothing. They evaporate.
And then the call becomes synchronous.
Yes. Sorry.
I know you're doing this for networked calls in remote procedures, but you can also do this locally across processes.
Definitely, right? Yes.
And again, the answer is probably it depends, because depending on your transport format, binary, JSON stuff, you've got layers upon layers. But what's the lowest latency you could get from one process to another if you say just did a binary blip?
I can't give you a figure, but basically you can communicate using, for instance, pairs of SPSE queues, and the speed at which you can serialize and deserialize and drain those queues. But you can have shared memory between them, so it's up to you.
Okay. And just perhaps another further question. If you have another process, say, waiting for that queue to be filled, what mechanisms does it use to be alerted that there's something in the queue, or do you have to spin on it? Or
Well, if you're using asynchronous, then you're spinning inside your executor until it gets executed. If you're blocking, then you're waiting. You've got some form of condition variable, whatever it is, sitting there, or you're actively polling some queue, whatever it is, on how you want to implement it.
yeah, okay, thanks.
Okay.
Any further questions? Going once, twice. Okay, thank you very much.
Thank you.